Hello.
Hi, Jitesh. Can
Hi,
you?
good evening. Good
Good.
evening, ma'am. You are host now.
Okay, thank you.
May I read?
Record शुरू करा के.
Recording started.
Okay, fine, fine. Hi. So, as because of your request, we have started. Like we will be covering this class in 3 parts. Fine. So, first part, I will take you through few of the topics, and second part will be covered by Dr. Dikshita, and third part will be covered by Danesar. Okay. So, because even stats is something which is not very, we are also very comfortable with, still, we will at least make you um, feel comfortable with your exam. Before that, in your chat box, I will just share the articles from which actually this exam they are being repeatedly like they have started asking you this question. So I will share the my article. Then I think corresponding faculty who will take your portion will share the article. So I've shared the article with you as well. So if you open that article, you will realize it is the core one. So can you see my screen? Yeah. So this is the core concepts in stats and research method. It has come in BJ 2025. So it has 3 parts. Part 1 and 2 has come up in January and part 3 has come up in May 7, 2025. So I will be covering the part 1. Dr. Dikshita will cover the part 2 and Danish sir will cover the part 3. Is it clear? So whatever information is there in this article, I will just go through all of them, give you a few concepts and also one or two more articles, which if you read is well and good, but it's I don't want to overburden you also as well. Okay, so to start with, I will be taking you through the basic terminologies, then we'll go through few validity tests, then what do you mean by the statistical inferences, then what is descriptive statistics, what is the normalcy of data, and finally the point estimate. So I will be taking you through this entire journey. So first is what is basic terminology. If you go through the points, there are few terms called as the observation. What do you mean by the observation of the data? Observation means refers to the pieces of information which is collected on individual patient. Okay, and each piece, suppose you are performing a study, like what you do is age 40 to 65 age patient, you are taking a height, weight, BMI, ASA, everything are the observation. Okay, if you pick up a age, that is a variable. Okay, and then when you say it has a number, okay, like it is between 40 to 65, the number that are called the parameters. And finally, because we cannot see when what is happening is, suppose a patient you are going to do a study on a patient who is undergoing a TURP surgery and you wish to check the effect of a particular drug. So you cannot do on the entire population. So we have a sample population. We assume whatever data we get from this population of 20, we are trying to extrapolate the same information on 100. So the 100 is the population mean and we are extrapolating from the sample mean. Okay. Are you clear on this 4 terminologies? Yes or no?
Yes, ma'am.
Okay. So next comes what is sampling error. So sampling error is like you try to estimate the blood pressure of a person. It came to be 120 upon 80. When you did second time, it came 130 upon 70. When you do multiple time and you observe the deviation is too high, that is called as the sampling variability or sampling error. Okay. So what is needed is called as the precision. Precision means if you repeat the test multiple times, the outcome that will come is the same. Then only you say that the sample will estimate the population parameter. Like suppose you are using NTG to decrease blood pressure. If you are repeatedly using NTG and each time with your use of NTG you see there is a drop in blood pressure, then only we can say this information of the sample can be extrapolated to that of the population. Then comes what are the data. So the variables whatever we studied are of two types. It can be numerical or it can be categorical. So numerical means either it can be again continuous or a counts. Continuous in blood pressure. Like repeatedly you can take the readings. If I say the counts means what is the number of episodes of vomiting, what is the number of episodes of headache. These are called the counts. When you look for the categorical, it can be nominal or ordinal. Nominal itself means what? Ethnicity, ABO blood group. So these are all the nominal data. Ordinal means like your scoring system, Likert 4 scale. Like I ask you how satisfied is you are with academic. So I ask you to rate me on a Likert scale. Very satisfied, just satisfied, neither satisfied nor dissatisfied, unsatisfied or highly unsatisfied. So this is called as the Likert scale and you can do the ordinal one. So this is the older way. The newer modern approach is, so what you see is you have to see a variable as two distinct valid values. That means if I say uh, are you are you feeling any headache? So the answer is either yes or no. If the answer has only two distinct values, it is called as the dichotomous variable. Okay? If no, then you have to look the order of the data is disputable. Like it has a like the order is there or not. If it is not there, then it's a nominal data, nominal variable. That is also called as the categorical variable. If you see the data has a fixed unit of measurement, okay, then it is a metric value. Metric itself means the number, like a scale. So if it is not a fixed unit of measurement, then it is called as the ordinal. So ordinal and nominal are the part of the categorical variable, and if you have a fixed way of measuring it, it is called as a metric variable. So what are the various scales of measurement? Whatever we learned, the same: metric scale, nominal scale and ordinal scale. Are you clear up to here?
Yes, ma'am.
Okay. Second, we will learn the concept of validity. So what is validity? Validity has two components: sensitivity and specificity. And then if you put together the sensitivity and specificity, they are called as the predictive accuracy. So what is sensitivity? Sensitivity, just remember true positive. That means it is the ability of the test to correctly identify all those who has the disease. So if I say in this population, tell me how many patient has tuberculosis. So if you are able to identify the test which clearly picks up all the true positive, that means the test is very sensitive. So you remember sensitivity is TP. So 90% sensitive means 90% of the disease person is screened by the test as true positive. Only 10% as falsely negative, means they had the disease but your test could not pick up. Specificity on the other hand is true negative. That means you can pick up, like it is falsely picking up. You are not having tuberculosis but the test is saying the patient has tuberculosis. So it is truly negative. So 90% of sensitivity means 90% of the here by mistake it should be specificity, means 90% of the non-diseased person that's screened by the test as true negative. Okay, then you go for a predictive accuracy that will reflect the diagnostic power of the test. So the predictive accuracy will depend on the sensitivity, specificity and disease prevalence. So when you get like you are asked to do a survey of a population, how many of them is positive with the test? Like if I say you do a Montics test, okay, and you want to see how many people of this population are actually positive or negative to pick up as a screening test. So if the test reads as positive, that means maybe 90% is truly positive and 10% is falsely positive. So the total will be the entire 100 people. If I say out of suppose 150 people, 100 were positive, so 50 were negative. Of the 50 negative, how many say 20 are falsely negative and 30 are actually truly negative? So it becomes the total again 150. Sorry, 50. Okay, so total positive becomes true positive plus false negative. Here, total non-diseased is falsely positive plus truly negative. Okay, did you get it this point? Suppose I say this is 100, this is 50. So total come is 150. Okay, of the 150, suppose I say 90 are truly positive, 10 have come falsely positive. And here, out of the 50, 20 are falsely positive, falsely negative, and 30 are actually negative. So, the total here comes 110. So, the test detected that 110 out of the 110, it detected only true positive was 90. Okay, and falsely negative for true positive and the person who didn't had the disease as 40. So according to that, if you further go, you have to remember few. This is the most important one. So sensitivity is the upper one. True positive by true positive plus false negative. Specificity is true negative by true negative plus false positive. That means they are just doing this box. They are playing with the one for the upper one for the sensitivity, second one for the specificity. Predictive positive test is true positive by true positive plus false positive. Mm. Okay, did you get it what I am trying to say? I just made one mistake. True positive, like sensitivity, you have to pick up only this one. True positive by true positive plus false negative. Specificity, you have pick up like this. False positive by false positive plus true negative. Positive predictive value, you have to take up this like this. True positive by false positive plus true positive. Again, for the second negative predictive value, you have to take the horizontal one. Are you clear up to here?
It's fine.
Then comes the statistical inference. So what is the importance of sampling is that what I already mentioned, that you want to, with the help of the sample, you want to get the information for a unknown population. So that is called as the statistical inference. So it is of two types. One is a parameter estimation, second is a hypothesis testing. Okay. So, parameter estimation is like you obtain a numerical value of the parameter from the sample and you try to project it to the population. And hypothesis testing means you are trying to get, like you are passing a judgment. This drug is acting on so and so disease, and it has an assumption like it acts on this and this disease. So you want to prove that what you're talking is true or not. So this is the hypothesis testing. Then something, it's a test of significance. So a very important aspect is to know if the deviation from the observed sample statistics and parameter value. Okay, and second is the deviation between two independent sample statistics. So you go for a testing. So by testing, we will the null hypothesis or alternate hypothesis. So it was first given by R.A. Fisher. Null hypothesis is a hypothesis which is tested for possible rejection under the assumption that it is true. Okay. So we will, and what is opposite is the is the alternate hypothesis. That means if you want to say that the melatonin acts on catheter related bladder discomfort patient or will reduce the pain of the patient in TURP surgery. So first you assume that it will not work. So the alternate hypothesis is it will work better than the placebo or it will work less than the placebo, but it is not equal to the placebo. So what you talk is equal to the placebo, that is your null hypothesis. Alternative hypothesis is either it is superior or inferior or it is not the same. Okay. So the alternate hypothesis will always use a two-tailed approach, either a left side or a right side, depending on it is more effective or less effective. So what are the errors in sampling? You can have type 1 error or type 2 error. So now we will come to type 1 error. So I mentioned you a topic like melatonin will decrease the incidence of catheter related bladder discomfort. So the hypothesis, it says it has no effect on catheter related bladder discomfort. So you did a study and you find there is uh, there is some effect. Okay, so you have rejected the, but because of your statistical problem, you rejected the hypothesis. You declared it as a falsely positive. So type 1 error is said to happen when the effect of an intervention is deemed significant. Okay, you mentioned that melatonin has effect, but actually there is no effect. Okay, or in other word, if you have incorrectly rejected the hypothesis or you are giving a false positive answer. Did you get it or you want me to repeat? Hello?
Ma'am, understood, ma'am. I don't know about this.
Dr. Anna, Dr. Nupur?
Yes, ma'am, understood.
Okay. So, when you are looking for a null hypothesis, so when you are going for a type 1 error, you look for the alpha. Okay. So, alpha is the type 1 error. So, as you increase the sample size, the p-value, I will come through it, the p-value will decrease. So 1 minus alpha is represent the specificity of the tests. So you have to remember here 1 minus alpha or the 95% is the specificity of the test. Type 2 error is you have wrongly accepted that it is true. So it is a false negative. Okay. So the error will happen when you say this intervention has no effect, but actually the intervention was effective. Okay. So it generally happens when the sample size is very low and variability is large. So the probability of type 2 error can be calculated and it can be started as beta. So this is what is the summary slide. If you don't wish to understand so much, at least at the end you can remember this as a brief. Type, the study accepts the null hypothesis. Okay, the null hypothesis is true, but there is no true difference. So here it will test the specificity and the if it rejects the null hypothesis when it was actually the null hypothesis was true and when like it's a falsely positive, so that is a type 1 error. But the hypothesis is false, there is true difference is there, but it accepts, so that is type 2. Okay, and if it rejects, then that is the power. So if you understand this summary slide, I think and your entire understanding means that this is a summary of the entire topic, what is type 1 error and what is type 2 error. Then comes power of the study. If you have seen this thing, so 1 minus beta is the power. So power of the study represent the sensitivity of the test. So 1 minus alpha is the specificity, 1 minus beta is the sensitivity. So power is the probability of correctly finding a given existence difference or effect as significant. So what happens, we generally keep arbitrarily a beta of 80% and alpha of 5%. That means if there is a difference or a effect that exists, there will be only 20% probability of type 2 error. Okay, so that is a maximum. The power is set to be 80 and maximum beta which is allowed is 20% error, beta error. Okay, so generally we have a greater tolerance, like alpha error is 5%, beta error is 20%, power is 80%. Why alpha error is given the highest priority, or always they try to keep it as low? Because alpha error is deemed to be the most serious error. Then comes, how do you calculate the sample size? So it is you calculated by the universal sample size calculator. What all you need to put in that? The minimum difference between the group, the standard deviation, then the type 1 error and type 2 error. Like I already mentioned, if you want a higher power, then it is like your beta will go to 10% and alpha should be always less than 5%. Okay. So if you put all the four information, you will get the sample size. And minimum difference between the effect size, if the minimum difference is very low, you need to increase the sample size too much, else the chances of type 2 error will be high. Okay. So minimum difference between the group, if it is low, then you have to increase the sample size. What is the standardized difference? That is the minimum difference by the standard deviation. That is called as the definition is called as the standardized difference between the group. Then what is p-value? So p-value or the probability value tells you how likely it is that your data could have occurred under the null hypothesis, or how likely you are to found a particular set of observation if the null hypothesis were true. So basically p-value is used in hypothesis testing, and what you have to remember is the smaller the p-value, the more likely you are to reject the null hypothesis. So you always tell the reverse in null hypothesis. So that is why p less than 0.05 is acceptable. The lower the p-value, that means you are to reject the null hypothesis and the alternate hypothesis is true. So this is how it is. So it is like the less the p-value, that you are unlikely to do anything wrongly false, like it is accepted. You have accepted the alternate hypothesis and rejected the null hypothesis. So there are something called as the superiority and non-inferiority trial. So what is the difference between the same? So in superiority trial, suppose I say I am doing a femoral nerve block and I am doing a saphenous nerve block. I say femoral nerve block is superior than the saphenous nerve block. So the hypothesis will be the femoral nerve block is equal to the saphenous nerve block. But the one other way of saying the same is femoral nerve block is not less than the, if you are talking about, there are two kind of trial. One is called as a superiority trial, one is called as a non-inferiority trial. I will give you an example. I think I will give a better example. So you know ESP, that is the erector spiny block. There is a new block that is called as the intertransverse process block, and there is something called as a paravertebral block. So when it comes to ESP and ITP, it is said that ITP is superior to ESP. And when it comes to ITP and paravertebral is any day superior, means it is assumed to be best. But in our study, we want to say that ITP is not inferior to paravertebral. That means it is equivalent maybe. Okay. So the null hypothesis will come that ESP is equal to ITP. When you compare between paravertebral and ITP, we will assume, because it has to say the reverse thing, so it will assume that the treatment, that is ITP, is less or equal to the paravertebral block. Okay. Then if the alternate hypothesis just says it cannot be, so it says it is not equal, either it is superior or inferior, but it is not the same. And here it will say the paravertebral is better than the inferiority, that is your ITP block. Okay. So if you are performing a type 1 block, that means you are saying when there is no difference exist, that time the null hypothesis is rejected. That means the treatment, deciding treatment is not equal to the control group. And when it comes to the non-inferiority study, you are deciding treatment non-inferior when it is inferior. Okay. So we want to say, because the same thing, when there is no difference exist, it is rejecting a null hypothesis. So in non-inferiority, we want to say it is actually non-inferior, but when it is inferior, it is saying it is non-inferior. So in type 2, reverse will happen. When actually a difference is there, it will say no, the null hypothesis is true. Similarly, when it is non-inferior, it will say that it is inferior. So the alpha 1 error rate, as I already mentioned, it is the same for either you are doing a superiority study or non-inferiority study. Alpha and beta, and the power or power is equal to 1 minus beta. Then next comes the descriptive statistics. So this we have already mentioned. Numerical data can be either metric scale, and it can be either continuous or count data. So you can summarize this using two things. The measure of location, they are called as the location parameter, and they look for they quantify the central tendency of the data, like where the data is clustered, and then the dispersion parameter, like how widely it is dispersed. So now we will go one by one. So first is the mean. So when I talk about the central tendency, that means whatever data you have, like this is your data. You like if I say the age, so I have 50 years, 60 years, 70 years, 80 years, 90 years. So you have over a range, you have the thing. So you want to see how closely they are clustered to each other. So mean means, suppose I say 40 to 100. So if I plot 1 and 1, if I ask you to find the mean, you will tell me just the arithmetic mean. Next comes the median. The median means whatever is given in your data, you will arrange them in the ascending or descending order, and you will just pick the middle number. Like if I say 1, 2, 3, 4, 5. So 3 is the median. Okay. So 3 is the median. So when the number of observation is odd, it is easy. Like 1, 2, 3, 4, 5, 3 is the median. Suppose I say 1, 2, 3, 4, 5, 6. So it is 3 plus 4 by 2. So that is your median. And next comes the mode. Mode is the one which is repeatedly most frequent repeated value in the distribution. Okay. And so it denotes the highest point of the frequency distribution curve, because it's maximum time distributed. So now comes what is dispersion. Then we will also get to know why to use median, what to use mean, and what to use, that I will come later. Then we'll learn about dispersion. That means if I say mean is 50, what is the average dispersion? Like suppose I pick up a study group between 20 to 30. So I say the mean was 25. So if I say 20 to 30, then I saw the lowest age which I got is 22, and the highest age which I got is 29. So dispersion will happen 25 plus minus 4.5 or 3.5, whatever is the lowest and highest. Okay. So it can be given by the few terms. Range. So first you have to find the central tendencies. This you have to keep in your mind. So this is a two-step, like how in data we always read as mean plus standard deviation, median plus interquartile range. So the location parameter is your mean, median, mode, and the dispersion parameter is your standard deviation, interquartile range, or coefficient of variation or standard error of mean. So these are the 5 types of dispersion. So coming to range. So what is range? It is the difference between the maximum and the minimum values. Okay. So suppose I pick up this. So you found the range because most of the result is between 45 to 68. Okay. But the range will come from 10 to 90. Okay. So range is very less used in statistics. Just you can say the range is wide or range is low. Second comes the interquartile range. Interquartile range is the range of the middle value, middle half of the value. That I will tell what exactly it is meant. So it is better measurement than the range because it only refers to the middle half of the result. Okay. So how do you calculate? So you have to place the same in a order. Okay. Then what you do is, because this number is a even number, total 8. So you split into group of 9 and 9. So you splitted this as one group and this as one group. Next, what you will do is, so if you see what is the median, so this time 1, 2, 3, 4. Here comes 1, 2, 3, 4. So on the middle Q1 is the 49 for this kind of data, this set of person, and here it is 62. Okay. So the interquartile range becomes Q3 minus Q1. Okay. That is 62 minus 49. So your interquartile range becomes 13. Right. Means the value becomes 13. So it is written median minus median means this will be the median plus minus the interquartile range. So Q3 minus Q1 is the interquartile range. I hope you got it.
Yes, ma'am.
Okay. Then comes the standard deviation. Standard deviation is more accurate than the range or interquartile range, but it takes into account all values and it is not unduly affected by the extreme values. So what does that means? Again, it means the dispersion or the spread of the figures around, and a large number of the standard deviation means a wide spread of the around the mean. Like if I say something 55, so if here comes 25 and here comes 65. Okay. So the dispersion will be high. So if the standard deviation is very high, that means what? That the values are over a wide range of distribution. Okay. So next comes, so there is a formula for the same. So this is the symbol that we use for standard deviation and this is the formula. Next comes the coefficient of variation. So the coefficient of variation is the same like standard deviation. Only thing is that instead of standard deviation, we will say about what percentage the spread of the data is there, like over 5%, over 6, 7%. So this is the spread of the data by expressed in percentage. Okay. So the higher the coefficient of variation, the more widely spread the values over the mean. So how do you find for the coefficient of variation? It is standard deviation by mean into 100. Okay. And then finally the standard error. So standard deviation or the is of a statistics is called as the standard error when you divide by the root of the number, the sample size. Okay. And finally, we will come to the thing is where to use median, where to use mode, means when do you use all this thing. So this is the summary of the location you have to see for the type of the variable. So I already mentioned metric. This is the categorical. This is your numeric. So if it is a categorical variable, then if it is a nominal scale, only thing which you can use is yes. Like mode, only thing you can use is the mode. Okay. If it is a ordinal, you can use both mode and the median. If it is a numerical, you can use all the three, but if it is a continuous, then you cannot use the mode. If it is a discrete number, you can use the mode, because in continuous you will not find a repetition thing. Okay. And then comes the dispersion. So if it is a nominal scale where you are using the mode, you cannot use any mode because mode is the only repetition. It doesn't has a range. If you are using a ordinal scale, so you are in ordinal scale, you are using both mode and median. So you can use the interquartile range as well as the range. Okay, standard deviation is usually given along with mean. So in metric scale, as I already mentioned, you can use all the three, and you can here also you can use all the three. Then comes when to use standard deviation and when do you use median. So if the data is normally distributed, I will come to the point also what is a normally distributed data. If the data is normally distributed, we use mean plus minus standard deviation. So mean is the location parameter and standard deviation is the dispersion parameter. If the data is skewed, I will come to you what is a skewed data. It is, we generally use median plus minus interquartile range. Is it clear up to here?
Yes, ma'am.
Okay. So now we will come to what is the normalcy of a data. So normalcy of a data, that means it is a symmetrical probability distribution where the data is clustered around the mean, and here the mean, median and mode all are equal. Like this is called as a normally distributed data. Suppose I say I have picked up a age between 80 to 65 for one study, and when I tried to see the age of the, like it's a spread between 18 to 65, I wanted to see what is the mean age of presentation. If it is between 54 and the lowest is also around 45 and the highest is between 60, it is very close around the mean values, then it will give a bell shaped kind of curve and it is called as a normally distributed data. If I see one is 65, one is 18, and the mean is mean is say 50, but the standard deviation is coming plus minus say 15 or 20. So 50 plus minus 20, that means it is a very widely distributed data. So it is a like it is a skewed data. So a normal data, it has a bell-shaped curve. There is one term which is called as asymptotic. That means if you see, these are the two halves where the mean, median, mode is same, but the tail end will never touch the x-axis. Okay. So this are the one of the property of the normal distributed data is the bell-shaped curve. Mean, median, mode are all the same. They are asymptotic. Other property are the half of the curve left and right will be symmetrical and the area under the curve will be equal. Okay. So the location is given by the mu, the median, and the dispersion is given by the term that is the standard deviation sigma. So how do you see a normally distributed data? So you can see it is a z, it is 0. So if you see a data is a normally distributed, that means if you see the midline, that is -1 to +1, okay, 68% of the data will be present in this between -1 to +1. Further, if you move ahead from -2 to +2, you will appreciate that 95% of the data is within this -2 to +2. So that is why always we write either mean plus -2 standard deviation. That means up to 95% of the data will be covered in this number. So what is for you to remember is that the standard normal distribution is a distribution with mean 0 and standard deviation of 1. Observations on the standard normal distributions is called as the Z. The area under the curve bounded by +1 and -1 standard deviation from the mean and plus and -2 standard deviation of the mean will cover 68% whatever I mentioned and 95%. when the critical value of minus 1.96, okay, or positive value on this side is plus 1.96. This is a critical thing. This is exactly the 95%. So if you go minus 2 to plus 2, it is 95.4. Exactly at a number of 1.96, it will correspond to 95%. Okay. So if this is the thing, then the probability of observing the Z with a magnitude of 1.96 is 0.05%. So here only you can appreciate p-value is 0.05. Then what is skewness? Skewness means the asymmetry in the presentation of the data. So either it can be a positive skewness where it is a right-sided, or it can be a negative skewness where it is a left-sided. So if it is a positively skewed, then the mode will be bigger than the median will be more than the mean. Okay. And if you see a negatively skewed data, then here you will see again the mode will be more than the median than the mean, and the mean will be on the left more side. Okay. So for that is why I mentioned for a negative, for first you have to check for the normalcy of the data. There are few tests, SAPIC Wipro test, and one more test is there, SMIROF something. Some tests are there who check for the normalcy of the data. If the data is normal, you pick up the mean plus standard deviation. If there is skewness of the data, which is non-normal distribution of the data, then you look for the median and interquartile range. So this is the summary slide. This is also very important for you. If the skewness is between minus 0.5 to plus 0.5, the distribution is symmetrical. If the skewness is between minus 1 on the positive side to minus 0.5, means anything between minus 1 to plus 1, that means the distribution is slightly skewed. And if the values goes between minus 2 to plus 2, which I already mentioned, it indicates substantial non-normality. So if the absolute value of the skewness lies between 2 in the positive or the negative, mean is the measure of central tendency. If the skewness is more than 2, then you have to use non-parametric test statistics like median to represent the data. Okay. Then comes what is the confidence interval. So you must have seen everyone write in 95% confidence interval. So confidence interval is the mean of your estimate plus minus the variation of that estimate. Okay. So this is the range of the value expect your estimate to fall between if you redo your test with a certain level of confidence. So you desired our confidence level is usually 1 minus the alpha value that is used in your statistics. So this is how you find. So 95% confidence interval. So plus minus 2% standard deviation if you take, then 95% of the data will be in that in between period. So the extreme data if you calculate, that is called as the confidence interval. Okay. And here 1 minus alpha is the confidence level which I have told you from the beginning. So if you are using a value p less than 1.01, so you have a confidence interval of 95%. So that is why always we have to mention what is the confidence interval. Then here you have to remember few points on confidence interval. Though more generally we do a 95% confidence interval, but a 99% confidence interval is even superior. Okay. And then it can be constructed at any point. So generally what we have when if you ask me, what I had a notion that confidence interval generally is spoken when you are talking about mean plus minus standard deviation. It is not the thing. Confidence interval can also be used for risk difference, relative risk, the ordinal ratio, or the difference between the mean. Okay. And one of the definition where most of the people think that the 95% chance that the interval contains the true population value, that is incorrect. It is nothing like that. Only the definition which holds correct is that the confidence interval means it is the mean of your estimate plus minus the variation of that estimate. So what are the various uses? So obviously the proportions, the difference between the means when you're estimating the variations or the population means. Finally, we will go to the point estimate. Are you clear up to whatever we taught? Or it is going above your head? Or you want a break? But we don't have time for break because 3 classes to go one by one. Should I go ahead?
Yes, ma'am.
Yes, ma'am.
Okay. So next comes a point estimate. So what is a point estimate? Point estimate is the value of the outcome of interest which is observed in the study. That means I want to read for the VAS score. Like I want to see the effect of one block on the analgesic efficacy. So I want to see the value of the VAS. So that is called as the point estimate. And then what you do, suppose I take a VAS score, I want to pick up the mean. That is the sample mean. So using that sample mean, I am doing the point estimate of the entire population mean. Okay. So the primary outcome, these are very important. Just try to focus it here. So the primary outcome is usually the magnitude of a treatment effect. So I will just take you one example. We did one study that was the effect of melatonin on catheter related bladder discomfort. Okay. So because there was no study before, so what we did was we put the melatonin along with a placebo, that is a vitamin C tablet. My primary outcome was to look for the incidence of and severity of CRBD that is reduced with melatonin. Okay. So I wanted to see the magnitude of the treatment effect. Like how good it is to reduce the incidence and severity of the CRPD, that is catheter related bladder discomfort. So this magnitude of the treatment effect is called as the effect size. Okay. And now how do we do that? Suppose I am picking up the VAS to know the effect of I am using the VAS code to know the magnitude of the severity. So the point estimate is used to make inference on the effect size. So for continuous variable, the statistical inferences usually require calculating the difference between the mean. Okay. So I have to pick up like how much it is able to reduce the VAS score from the placebo. So I have to pick up the difference of the mean. So a few things you have to remember here. Suppose I am doing a intervention. So there are two kind of things. I am talking about the incidence. Incidence is generally given in yes or no. That is a binary outcome. Severity has a grading. That is a continuous outcome. So if I have to look for the incidence of CRBD, I will try to pick up the relative risk and odds ratio. If I have to see the severity of CRBD, I will pick up the relative risk reduction, absolute risk reduction, and the mean difference between the group. So what is, if I'm talking about a binary outcome first, what is a risk difference? So if for the risk difference, suppose I again say the intervention group was a bromocriptine, melatonin, and the control group was a vitamin C. What happened to the event of CRBD? It happened? Yes. So A. Okay. It didn't happen. So no event. B. With the control C and D. So the risk difference is A by A plus B minus C by C plus D. So this is called as the risk difference. What is the event rate? How much? So in general, it is called as the event rate. That means how much, in how many patients this event happened. So difference in the event rate between the two groups. Second is relative effect size. So if you divide the risk difference by the event rate in the control group, okay, that is called as the relative effect size. Third term is what is relative risk. Relative risk is what is the probability or the ratio of the probability of the event happening in the intervention and the control group, means A by A plus B by C plus D. So risk difference was minus risk, relative risk is division. So 3 interpretation. If relative risk is 1, that means there is no difference between the two. Okay. And second is, if it is less, that means less than 1, that means the observed risk was less with melatonin than the placebo group. If the risk was more than 1, risk ratio is more than 1, that means the incidence of CRBD was higher in the melatonin group than the non-exposed group. So we generally desired, if you want to see, a relative risk of less than 1. So once you have understood the relative risk, then we move to odds ratio. Odds ratio is AD by BC. Okay. Here also same, if odds ratio is 1, that means the incidents are the same. If it is less than 1, that means the intervention group was better. If it is more than 1, that means the incidence of the intervention group was bad. So a question comes, what is the difference between the risk ratio and the odds ratio? If both the same is 1, 1, 1, what is the added advantage of having a risk ratio over the odds ratio? Why I'm trying to focus is because of the article I first shared in the group. The same article, they have written this part in very great detail. So that's why I'm also detailing you a bit more. So it has relevance in 4 points. One is baseline event rate. Second, it categorical labels. Third is statistical properties. And fourth is case control studies. So we will go one by one where odds ratio is superior to the relative risk. So what happens when the event is very rare, less than 10%? That time there is no difference between risk ratio or odds ratio. But if the event rate is common, then they are dissimilar. Okay. So, like when RR was more than 1, that time when the event is common, like it's a very common paracetamol, suppose I don't, because CRBT is a rare thing. So, if I say paracetamol and fever, so event is very common, but you found that paracetamol was associated with increase in the number of fever episode. That time odds ratio will provide a more useful measure of the strength of association than RR. So, this is one condition where odds ratio is superior to relative risk when the event is common and relative risk is more than 1. Okay. Second point is category label. So what happens? You are comparing one with the other. Both are active. You are comparing between melatonin and say hyoscine. Both are an active treatment in CRBD. Now what I did is I just reversed the group. If you reverse the group, so if you look at the numbers, so a by yeah a by n1 means a plus a by a plus b by c plus d. So if you reverse it, odds ratio will relative risk will change if you change the labeling. But when you compare the odds ratio AD by BC, this will not change. That is why if you want to exchange the labels, that time odds ratio proves superior than the relative risk. Okay, this is the second condition. Third condition is statistical property. The if you want to go for an attractive statistical property like logistic regression, exponential value of the regression coefficient, you go for a odds ratio than the relative risk. And finally, case control study. So in case control study, you always go for a odds ratio over a relative risk. Okay. Did you get it? So these are the 4 conditions where the odds ratio is superior to the relative risk. Case common, relative risk more than 1. When you are trying to change the labels, Third is statistical, when you want to go for the advanced stats like logistic regression, exponential value regression coefficient. And finally, the case control study where OR is a better than, where you cannot use the relative risk. It is the OR which has to be used. Second comes, if you would have remembered my first slide, I told I am going to cover in 2 points. One is if the study, the intervention study has a binary outcome. So binary outcome is given by the relative risk and odds ratio. If it is a continuous outcome, like I want to see the effect of melatonin on the severity of CRBD, that time I will use the relative risk reduction, absolute risk reduction, and mean difference between the two. So now we will study the second part. The continuous variable. So in continuous variable, what happens is it is called as the relative risk reduction. That is 1 minus the relative risk. So if you look at you found the relative risk, suppose the relative risk came out to be 90%. That means the relative risk reduction will be 10%. Okay. Second is absolute risk reduction. Absolute risk reduction is the control event rate minus the experimental event rate. Okay. And how do you calculate for the control event rate is, suppose as I already I gave you placebo. So, and I'm looking at the severity of CRBD or the incidence of CRBD. So what I will see is the number in the control group with the event was 90 and total patient were 100. So the risk in the control group is 0.9. Similarly, in the experimental group, the person who received melatonin, it came to be 60%. Okay, so 90 minus 60, so is equal to 30. So there is absolute risk reduction of 30% and relative risk reduction of 10%. Did you get it or you want me to repeat?
Ma'am, repeat, ma'am.
Okay, there are two things. Relative risk reduction is 1 minus relative risk. Like I mentioned the experimental group. So what happened? The patient who took the medication, their risk, like the incidence was, suppose the relative risk was 60% or 0.6. Okay. So the relative risk reduction will be 1 minus 0.6, that is 0.4. So it got reduced by 40%. So the one which was supposed to be 100%, now it has reduced to 60%. Means what? The reduction has been by 40%. No. If you have scored 6 out of 10, 6 is your relative risk. Means that number is relative risk. So what is the relative risk reduction? How much, by how much mark your score has come down? By 4, no? Dr. Saravanan.
Yes, ma'am. Yes, ma'am.
When I come to absolute risk reduction, suppose there is a student in your school who was very good in study. So rather it won't come in the correct way. Okay. Suppose you like how I was giving you incidence of melatonin and placebo vitamin C. So in the patient whom I gave placebo, what I found is there was a reduction, like 90% of the people didn't complain. 90% of the people complained of the symptoms, 10% didn't complain. Okay. So the control event rate, how many patients having CRBD was 90%, right? 90% of the people who got vitamin C had CRBD. In the other group whom I gave melatonin, 60% of the people had CRBD. So the difference between the two groups is the absolute reduction rate. Am I clear now?
Yes, ma'am. Yes, ma'am.
Okay. Finally, one more point is what is called as the number needed to treat, NNT. This is also one of the very favorite question of the examiner. So the number needed to treat is the number of patients that would need to receive the intervention to prevent one bad outcome. That means if you treat 20 patients, minimum, suppose what you do is you just picked up I picked up a sample size of 5 and I say none of the patient had headache. Okay, none of the patient had sedation. But that doesn't mean that if I go to 30 people, none of the patient will have any bad outcome, no? So that is a minimum number of patients that you should give, you should receive the intervention to prevent one bad outcome. That is very important in statistics. Second is number needed to harm. That means the minimum patient that would need to receive the intervention to cause one bad outcome. That is prevent one bad outcome. This is to cause one bad outcome. Okay. So NNT is more important. It will involve a more number of patients. Just you remember this is the only difference. Prevent one bad outcome and NNT is to cause one bad outcome. And don't tell me what is the difference. It is statistics. Okay. So the NNT is won by the absolute risk reduction. So this defines a causal relationship between the intervention and the outcome. So this is all the part of my whatever I was supposed to teach you. So I will take you quickly through this. So if you go one by one, this was the first part which I was given to teach. So we have spoken about what is observation, what is variables, then what are the probability distributions, what is this mean, this thing, what is parameters. Then I took you to sampling variability. Then what are the types of data, what is nominal, numerical, the ordinal, and all those data. Then we spoke about what is the measures of location, what is central tendency, what is the methods of distribution, what is mean, median, and mode. Then we spoke about this, I covered in a huge detail also. I will tell you why. Then point estimate we had discussed. Okay. What is effective size? And this is the box I picked up. What is risk difference? What is relative risk? What is relative risk ratio or risk ratio? What is odds ratio? What is NNT? Then what is the difference between relative risk and odds ratio? Okay, this is how a normally distributed curve and what is the difference between skewed data and a normal data. So what is the normal data interpretations? This was the box I was talking you. Then what is standard error of mean? What is the sample differences? Then what is the null hypothesis? What is p-value? Then finally, these are 2-3 things which I don't think is important. And finally, I picked up the confidence interval and all these points. I just try to simplify it so that you will understand it better. I will give the article as well. So apart from this, I too covered 2 more articles. Just 1 second. Stats. Data interpretation. Just give me 1 second. Actually, I'm trying to figure it out which articles I have to share. Yeah. So this is one article. What are the statistical sample size and power? What is type 1 error? What is type 2 error? What is the power of the study? How do you what are the minimum things that is needed to get the type 1, type 2 error? Standard difference. So this is one article which we too covered, and one more article is there. Is that clear? Any doubt from any of you?
No, ma'am. Ma'am, I just wanted to ask, like, because I did read stats little bit for the part one. Is it required in such extensive manner, like, or just basic?
See, what has happened is I will just tell you. Initially, when we used to give, I was giving exam, they were just asking the podcast. Okay.
Mm.
So that was podcast means your whatever Zima blanket has given. But recently, what information we got is they have asked about the advantage and disadvantage of each of the study. Okay. They have asked you how do you calculate a sample size.
Mm.
So, and these are directly from these articles, whatever I showed you. These are directly copy paste. This means Dr. Dikshita will take you to part 2. Few the sample size methods and calculation, whatever I taught, they're directly asking. So it is not
Mm.
the extensiveness which you need. You just read the article because my job was to teach in a way so that things will get simpler for you and you know what to focus when you are teaching reading. Because reading the article, interpreting near to the exam is not that easy, especially statistics.
Yes, ma'am.
Just my
Yes, ma'am.
job was to make it simplify and then I will share the article. Just you read those 3 articles, not more than
Yes.
that.
Yes. Thank
Okay.
you, ma'am.
Yeah. Dr. Dikshita is here. So I will make, hi Dr. Dikshita, how are you?
Hi, can you hear me?
Yeah, I can hear you.
Okay.
Yeah, so I have covered the part 1 for them. So
Mm-hmm.
you can go ahead with part 2. And
Yeah.
I've shared one article as well. So when you're near to your completion, no, you have to call sir.
Okay, sure.
Okay, bye bye.
Bye-bye. Thank you.
I'm leaving. Just you check.
Yeah.
I'll leave.
Yeah. You made me the host. Thank you. Okay. Good afternoon. Good evening, everyone. I mean, I think only there are 2 people.
Good evening, ma'am.
Good evening. Good evening. So who are with me? Just a second. Okay, Dr. Nupur and Dr. Saran. Okay, fine. So since we prepared this short session for the statistics, whatever possible questions or the topics or the discussion which can be done, we have tried to divide it into 3 topics. I think quite a chunk of it, Dr. Amrita has covered it already. Now I will cover the second part of it, and the third part Dr. Danish will be covering. Okay, fine. Just a second. Is the recording still on? Okay, fine. Okay, so I'll just share my screen. We will just discuss as it goes. Just a second. Okay. You're all able to see my screen?
Yes, ma'am.
Just a second. Is there a possibility I can present in this itself? I don't think so, right? I think I have to just share and present. Fine. Okay, fine. So I think the major variables and everything we would have covered in the first session. Now we will just study the type of various clinical research, the various types of studies, which is observational and the experimental studies, and how are the various bias which can happen. How can we do the steps to reduce this bias or the confounding variables? Okay, there are certain analysis and certain techniques with which you can reduce this bias. Okay, so first and foremost, as we can see here, you all can see my screen, right? Okay, so we can classify it as primary or secondary research. Okay, what I mean by primary research is the first time a particular concept is being studied. Okay, so obviously you're going to first time, since you're going to do the topic for the first time, then you're going to collect the data for it. Okay, and this can be either an observational study wherein you're not going to do any intervention, you're just going to observe whatever is happening in it. As in, you have you have an exposure, you will either prospectively follow it to the outcome, or you already have an outcome, then you retrospectively follow and find out what are the exposures the patient would have had. Okay, so this is kind of observational studies. The next is your experimental study, what we do routinely. That is, we do an intervention and look for the outcome, whether it is better or not. For example, nowadays we do a lot of researches on the various regional blocks, right? So to see whether this is going to have a better outcome or not, and then that is called as an experimental study. Okay. Secondary research is when the study has already been done. A lot of studies have been done. Okay, so ultimately they tend to do a systematic review, a meta-analysis, review article, all these things which is done is what is called as a secondary research. It's a complete analysis of various RCTs or various case control studies, various cohort studies, all together is called as the meta-analysis. Clear? So this is the broad classification of your clinical research as such, an observational study and an experimental study. Okay, now experimental study we will discuss in the next session. So here it is classified as the randomized trial and the non-randomized trial, which you all know. So moving on to observational study, which will be my main focus of discussion in this session, is descriptive and analytical. So when I mean by descriptive, you're not comparing it with any other group. Okay, so it is either a single case report, okay, or a series of similar cases which is reported as a case series, or it could be a cross-sectional study wherein both cross-section means at one point of time both the exposure and the outcome is measured. Okay, the same thing can be an analytical study wherein you're going to compare with something. So it is either descriptive where there is no comparison, or it is analytical where you use a comparison. So in the comparison, we have majorly two types. One is the case control study, another one is the cohort studies. Okay, case control study is again, usually the outcome is already done, is already there. So you have the patients with the outcome. For example, you have patients with lung cancer and you check for these outcome patients for the exposure of smoking or not. You do a retrospective analysis. So that is case control study. The other one is your cohort study, wherein you start from the exposure and you prospectively follow up the patient. It can be a retrospective cohort study also. There are certain retrospective cohort studies also. But what we majorly do is your prospective cohort studies. Now, whenever we do such a study, okay, so as I told you, this is observation, okay. So when is case report or case series done? Obviously, if it is going to be something rare condition, okay, so it is better to publish it as a case report or a case series, wherein you're not going to get a large number for you to make it a proper study. Okay, so in that case, you say it as a case report or a case. So it's very useful when you're going to study something which is rare. Okay, then moving on to the cohort study is something wherein the group is based on the exposure. But the problem with the cohort studies is that you need to follow up with them with time. So there can be a lot of attrition loss. That is, the patients might not come for the follow-up. So you lose on your sample size as well. Then the case control study wherein you already have the outcome. You just have to do a retrospective analysis to look back for the exposures. Okay, so these are the main types of your observational study. So they might ask you on how do you compare a case control. For example, they might give you an example and they might ask you whether it's a case control study or a cohort study first and foremost. Okay, so as we've already spoken, case control is based on the outcome is already there and you're going to check whether the exposure is there or not. On the contrary, your cohort study, you're going to start from the exposure status and then follow up the patient. Okay, so the case control is majorly a retrospective and this is going to be a prospective study. Okay, so and in the case of data collection, you already have everything ready. You just have to follow up on the files backward and then you have to check up on it. Okay, so and obviously this is more useful if you use a rare study again, because you have the number of cases already and you can check on what are the possible risk factors they have had in the past. And the outcome is usually measured for case control study as an odds ratio. Okay, while on the contrary, for your cohort study, the outcome is measured as a relative risk. So these are the questions they can ask. It's measured as odds ratio in the case of case control and relative risk in the case of cohort study. Okay, so is it clear? Is this difference is clear for both of you?
Yes, ma'am.
Yes,
Yeah.
ma'am.
Moving further, so this is just for the completion's sake. I have actually prepared this PowerPoint from one of the important BGA articles. Okay, I will share that article also. So just for the sake of completion, any ethical research, okay, the various principles that should be followed in it are, it should be autonomous, okay, it should be beneficial or maleficent. That is, you should do good. And of course, just because you're intervening in one particular set of patients, and if you're not intervening, the other set of patients should not be at harm. Okay, if these patients are at benefit, that's okay. And the other patients, they have been following the routine treatment, it's fine. But they should not be at any specific harm due to the intervention. So basically, they should be beneficial and non-maleficents. Okay, and of course, there should be good selection of patients so that you can remove any kind of bias involved in it. And finally, you need the ethical approval, which is mandatory. So whenever you do a study, there are various types of bias. Okay, there can be your selection bias, your attrition bias, your measurement bias. Okay, observe as you see here. Now, what are these various types of bias? Okay, well, when you have a selection bias, suppose you take a sample which is not reflecting your target population. For example, we have done a study, say, in patients in the probably in Asia, okay, and we reflect this, or we use this conclusion of this study to a European population. It might not be very effective. Okay, and hence this is called as the and if you have to completely transparently relocate the entire study to the European population, there might be a lot of bias in it. So basically, your study sample should be representative of the target population. Okay, and this sample further you need to, and because in your observation you're not doing any randomization. Okay, so you need to you'll encounter a lot of confounding factors. What I mean by confounding factor is like a common factor. For example, obesity, like you're studying a group of patients with diabetes, hypertension, and the risk of cardiovascular, major perioperative cardiovascular events. Okay, in these group of patients, a confounding factor will be, for example, your obesity, your BMI. Now, this BMI, it is not directly related to your the exposure, nor is it directly related to, or it can be related to both. Either it will not be directly related, or it can be related to both your exposure and outcome. So these are some bias called as the confounding bias. So what will happen? Obviously, the ultimate interpretation of the study will be affected. Okay, so the various types of bias are selection bias, wherein the study sample is not exactly representative of the target population. Okay, so this will obviously compromise your validity. For example, another example I'll give you. Suppose we do a post-operative questionnaire, okay, and you do it, suppose we do it in a literate population. Okay, so they are able to tick and respond to all the questions in the questionnaire. Post-operative, suppose anesthesia awareness after general anesthesia. So they will be able to respond to all the questions. And if the conclusion of this is generalized to a population wherein they cannot even interpret or they cannot tell this, then obviously there is selection bias. The second one is the attrition bias, which I told most commonly happens in the case of your cohort studies, wherein you have to follow up them. So there can be a loss in between. The patients might not come for the follow-up. That is attrition bias. Okay, then you have the measurement bias. So measurement bias, for example, you are doing, again, you're reporting the awareness under general anesthesia, okay, for inpatients, and you're doing it for daycare patients. Okay, you're doing a study. So you select a set of patients who were operated on a particular day, and they were, suppose one group of patients were daycare and one group of patients were still inpatient. Okay, so the inpatients will be able to recollect better compared to your daycare patients, unless it was really traumatic. I mean, they were completely aware. Then the remote daycare patients can also recollect. But if it is not much, then the inpatients can report better because they are post-operatively in the hospital. They are reflecting the pain scores, everything. So this is one kind of measurement bias. So you need to, if you're doing it, then do it only for the inpatients, or if you're doing it, or do it only for the daycare patients. Okay, so that is with regards to your measurement bias. Then coming on to your observer bias, wherein the person who's doing the study, okay, for example, you're doing a gastric focus, okay, so in the and you're doing a study based on gastric focus. One anesthetist might interpret it as grade 1, and the other anesthetist might tell, no, this is grade 0, or they might even say this is grade 2. So this is called as the observer bias. Okay, so they can just give you such examples and say what kind of a bias can happen in this kind of a study. Okay, so that is one thing. Now moving further, how can we minimize these bias or confounding factors? Okay, so there are various techniques. I will describe each of these techniques one by one. That is matching, stratification, regression analysis, propensity scores, and instrumental variables. So one thing you need to remember here is the first 4, okay, they are all for known variables, as in you have a measured variable which you can reduce the bias by segregating the groups which have the same property, and then you can reduce the bias. So the first four, that is matching, stratification, regression, and propensity scores, they're all for known variables. If you have to reduce the bias due to an unknown variable, then you can use the instrumental variable analysis. I will explain all these things. Now, moving on to the first thing, which is matching technique to reduce your bias. Okay, so now what is the purpose of this? You need to reduce the various common variables. Okay, so that you bring the patients with the common variables equally distributed in both the groups. Okay, either you do equal distribution, or you say if you put them completely in one group, then again that becomes a confounding factor. So you have to basically, based on their age and comorbids, you have to equally do it. So this you can do either as an individual matching. Each case is matched, okay, with the control. For example, as I've given here, a patient with diabetes and smoking status, okay, they're undergoing CABG. Now this should be matched with the same profile patient in the control. Okay, so that both the confounding factors are removed, negated. The next technique is you're doing the frequency matching. Okay, wherein again you distribute all the to both the groups. Okay, you make a group of patients with the confounding factors, and you make sure there is equal percentage of the patients with the same properties in both the groups. Is that clear? Just let me know if I'm a bit fast, because these topics are quite dry. I don't want you to spend much time in this, because I know all of you are having exams nearby. When are your exams, by the way, both of you?
Mine is in July.
July. And Dr.
Mine is
Nupur?
8th June. 8th June.
June, yeah. Yeah, because that's what I heard, that most of them are giving in May end and June first week. So we don't want to spend much time in this. Just catch the important points and go ahead. That's it. Okay. So basically matching, we do it either by individual matching or frequency matching. Okay. And obviously the benefit of this is that you're trying to reduce the bias due to the known confounders. Okay. As I told you, the first four, which is for known confounders. So finally, you ensure there is a baseline comparability between the two groups. Okay, so that your final interpretation is not much affected. So that's the first technique. The second technique is your stratification. So what we do in stratification is that, again, instead of earlier in matching, we were dividing it as 40% in both the groups. Here, what they do is you stratify the various confounders. For example, you take people of BMI category, first you stratify them. Okay, and then you divide them into the two groups. Okay, similarly, the people of the sex, male sex and female sex, again, you divide them and distribute them equally. So you stratify them first, and then further in each strata, you're going to distribute them. Okay, but the problem with the stratification is that it again works only when one or two factors are present, one or two confounders are present. Okay, what happens if you have more than two confounders? Okay, that's when your regression analysis comes into the scene. Okay, so for example, one second, I'll just play this right. Okay, so this is one example of your regression, your stratification. What example? As I've shown in this, you have patients, you want to diagnose the risk of diabetes mellitus being associated with surgical site infection. Okay, so obviously the confounder here is your BMI. So without stratification, you might just say that, the SSI rates between diabetes and non-diabetic patients, you will find a particular rate. Okay, but we know that diabetes can be more common in the case of obese patients. So to remove the confounding factor, first you stratify them based on the BMI. Then within each BMI, finally you find out the SSI rates. And this you further classify as diabetics and non-diabetics. So first you divide them as based on BMI. This BMI is further divided into diabetics and non-diabetics. And then finally you find the incidence of your SSI. So this is your stratification. Is this clear?
Yes, ma'am.
Yeah, because I am trying to incorporate an example with each of these techniques so that it will be a bit more understanding compared to just reading out the theory part of it. Okay. So next is your propensity. Okay. How do you do the propensity scoring? Okay. So for example, let me go to the example first. Oops, I didn't incorporate that example. Sorry. Okay. So what happens in propensity is that you based on the each factor. Okay. You, one second, I'll just find, I had taken the example, just a second. Let me just share that also. Okay, not really able to find it, but what I have it in my phone is that, one second. Yeah, so in propensity scoring, so that is another technique again to reduce your bias. Okay, this is again limited to 1 or 2 confounding factors only. So what you do here is that, again, based on the factor, like for example, age, okay, you divide them, okay, and you assign them a score called as by logistic regression. What I mean by logistic regression is, for this logistic regression is usually for binary outcomes. For example, live or dead, okay, male or sex, I mean male or female. Okay, so this kind of binary outcomes, they are usually given a score as 0 or 1. Okay, and this is via logistic regression analysis. Okay, so what you do is, first you estimate the probability, like the different classes of groups, for example, age, BMI, or the ASA status, okay, or the comorbids, whatever be the variable you're using. Okay, you calculate the logistic regression for them. Okay, that is, you analyze the different percentage of the people, and then you give them a score of 0 to 1. Okay, and then this is further matched. Okay, people with the propensity score of 0 are categorized in one particular group. People with the propensity score of 1 are categorized into the other group. So in broad terms, or important concepts in this, just remember this: propensity scoring is another technique for reducing your bias in the case of observational studies. Point number 1. Point number 2 is that, based upon the various parameter you're analyzing, usually it is a dichotomous variable which you're going to analyze, which is either age or the sex, okay, or your ASA status, whatever, it's a discrete value. And that is given a score of either 0 to 1. And based on the scores, then they are further stratified, okay, so that you can have a proper matching done with them. Okay, so this will reduce the bias. So this is another type of technique to reduce your bias. So until now we read matching technique, then we read stratification technique, and now we have read propensity technique. Okay, is that clear? I know it might not be sometimes very interesting. In fact, it was not for us as well when we had to prepare for this session, but we are trying to cover the maximum for you people. Is there any doubts, or you want to contribute anything at this stage of this discussion?
No, ma'am.
Okay. Okay. So as we told, until now, we are all, the only limitation with all this kind of techniques is that we can only do this for measured confounders. Okay. The unmeasured confounders, for example, anxiety, all these kind of things where you cannot measure it. So those confounders you can do by a different technique. Okay. That is your last one, instrumental variable analysis. So before that, we will do the final technique, which is your regression analysis in statistics. So regression analysis is used. So the previous 3 could be used for up to 2 to 3 confounding variables. If you have more than that confounding variables, or more than that variables which might cause a bias, then you use this something called as a regression analysis in statistics. So what do you do in regression analysis? Okay, so here we have to find out the relationship between the dependent variable, that is the y. Okay, y is the dependent variable, which depends on your independent variables, which is your x1, x2, x3. Okay, what I mean by the independent variables is here again, age, your sex, all these are independent, which is not going to depend on anything. But the final outcome, or patients with diabetes, patients with hypertension, all these are your independent variables. The final outcome of y, whether you have a perioperative event, major adverse cardiac event, will depend upon so many such independent variables. So when you have many such variables, how to reduce the bias? That's when you use the regression analysis. So simple linear regression means, suppose you have y is equal to mx plus c. Okay, that is only one unknown variable. In that case, you use a simple linear regression. You have multiple linear regression, you use this. Okay, this formula. Okay, and if you have a logistic regression, as I told you, a binary outcome, then you use the 0-1 scoring. That's it. Okay, so this is the 3 types of regression analysis. Now, based on this, as you see here, the coefficient just shows the degree, the strength of association or the direction of association. If beta 0 is, beta 1 is going to be positive, then it is a positive linear association. Okay, if beta 1 is going to be negative, then it's a negative linear association. Okay, so these are the, so depends upon the direction of association and the strength. Okay, R square is again, so these are the various other final outputs which you get from this regression analysis. So you can get your p value here and R square. R square is the percentage of the final variance you get. So ultimately what you need to know in this regression analysis and statistics is used when you have more than 2 confounding variables, or even single confounding variable you can use, but is usually used when you have multiple confounding variables. And what do you use? You use the multiple linear regression technique. Okay, and wherein the formula is usually the outcome depends upon your coefficients. Okay, and each coefficient into the each dependent variable, addition of all these, and finally your epsilon is your error or residuals. Okay, so until now we studied matching, stratification, prospective scoring, and your regression analysis. So all these 4 techniques are for your known or measured variable. So moving to the last technique, which is your instrumental variable analysis. Okay, now this is a statistical method which is used for your unmeasured or the confounding variable. Okay, unmeasured confounding variable. Until now we measured the we were doing the techniques for your measured confounding variable. For your unmeasured confounding variable, you use this instrumental variable analysis. So how do you use this? I'll go to the example first. For example, you have patients who are close to a hospital. Okay, and they close to a hospital wherein your labor epidural services are provided. Okay, and you have another set of patients who are close to a hospital which is not a tertiary center, which is just a basic center wherein they do not provide labor epidural and all. So the distance to the hospital with epidural service, though it is related to the exposure, it is not related to your outcome. Okay, so as you see, the effect of your epidural analgesia on labor is going to be associated with the exposure. It is not directly associated with the outcome, and it is not related. So what I'm trying to say here, come back here. Remember this example. Now based on this example, come back here. So this instrumental variable will be associated with both either the exposure or treatment. It will not be directly associated with the outcome. Okay, and for this kind of unmeasured confounding variable, you can use this instrumental variable analysis. Okay, so basically they use a lot of formulations in this, and the statistical analysis is done, and finally you get the value for it, which is not of our interest. But you need to know what kind of a technique is used for the unmeasured confounding variable, and that is instrumental variable analysis. Okay, so propensity scoring, matching, stratification, regression, these all are for known confounders, while your instrumental variable analysis for your unknown confounding factor. Okay, is it clear until now? At least about 20-30% of what was discussed. I will give a rapid review in the end. Okay, fine. Now, finally, how do you interpret these observational data? Okay, there are 3 important terms here: association, correlation, and causation. Okay, so association is that when the variables relate, but they're not there is not a causal relationship between them. For example, people who snore are more likely to have hypertension. Okay, so snoring gives you an information that they probably have the chance of hypertension, but does not mean that snoring can lead to hypertension. Okay, so this is association. When two variables, they occur together in a patient, okay, and they are so frequently associated in various patients that they might be thought as a causal relationship, but they're not causal. They're just found by chance together. Okay, so that is for your association. The next one is correlation, wherein you have a linear relationship between the variables. For example, as the BMI increases, the probability of OSA increases. Okay, so this is for your correlation. And I think Dr. Amrita would have already discussed about the normal data, right? The skewed data, the normal distribution and all. So here you use the Pearson's rule to find the correlation analysis final data. And for the skewed data, they use something called the Spearman's rule. Okay, so these are the two rules. Okay, and correlation does not definitely mean causation, but it has some linear relation, as in people with increasing BMI tend to have increasing severity of OSA. Okay, so this again, there is some linear relationship. The final one is your causation, wherein one variable directly affects the another. Okay, for example, a patient with OSA, okay, are at increased risk of postoperative pulmonary complications. Okay, so one variable, when it directly affects the another, it's called as the causation. So the various interpretation of observational data has to be again classified as association, correlation. Correlation can be linear correlation, which can be in the positive direction or it can be negative direction. And finally, you have the causation. Okay, and finally, once your observational study is done, you report it. Okay, so when you're reporting it, there are certain already prescribed guidelines which should be used if you're going to use the observational studies, which will help increasing your publishing in your high impact journals. So that is, one is equator network and the other one is your strobe statement. If you use the checklist or the guidelines prescribed by these two networks, equator stands for the enhancing the quality and transparency of health research, while strobe stands for strengthening the reporting of observational studies in epidemiology. If you use these two guidelines, then you stand a better chance that you have covered all the possible techniques to reduce the bias. Okay, it gives a good checklist, and thereby you have had a transparent technique, you have followed the ethics of the various research principles. Okay, and then you have been able to complete the study in a proper documented way. So this is the reporting standards. Okay, so to brush up fast, before that, I'll just give a reminder call for Dr. Danish once again. Okay, so to sum up, okay, just what is required for us for the exam point of view is that what are the various types of study, whether it's a primary research or a secondary research. Okay, you know this difference, right? And primary is further classified as observational studies and experimental studies. One which is done for the first time is a primary research. All kind of meta-analysis and systematic reviews are your secondary research. And this classification we know. So here again, to be more focusing on the observational studies, which is my topic of discussion today. Here we're going to divide it as descriptive and analytical studies. And descriptive is further divided as case report, case series based on that. And these type of studies are more useful when you're using a rare parameter, a rare disease, a rare exposure, whatever it is. Okay, but basically a rare outcome. Okay, while your cohort and case control studies, wherein it is more common and you need to find out the incidence or prevalence, whatever it is. And case control is mostly a retrospective study, wherein you're going to start from an outcome and go back, study the exposure status. On the contrary, your cohort study is going to be a prospective study, wherein you're going to start from the exposure and go prospectively. So the problem with cohort is your attrition bias. Okay, there can be a lot of follow-up loss. Okay, and in both case control and your cohort study, you can do the comparison wherein you're going to study what are the outcome is measured as. Outcome is measured as odds ratio in the case of case control study, while it is measured as a relative risk in the case of your cohort study. Okay, fine. Then moving on to the prints, this is nothing. Yeah, going on to the types of bias which can happen: selection bias, attrition bias, measurement bias, observer bias, and confounding bias, the various types of bias. Okay, and how can you reduce this bias or the confounding factor? By 5 techniques, which is matching, stratification, regression, propensity scores, and instrumental variables, out of which the first 4 are for measurable variables, while the instrumental variable analysis is for the unmeasurable confounding factor. The first 2 is for usually 1 or 2 confounding factors, while your regression and propensity scores are for more than 2 confounding. And regression majorly is for multiple confounders, wherein you use that formula, and based upon each variable, how is that confounding factor, you use a coefficient and you get the final regression analysis done. Okay, so these are the various techniques for the matching, which is your individual matching and frequency matching, which I've already described in detail. And stratification, you stratify the various patients. For example, you have to study a particular outcome, then you divide that outcome as diabetic and non-diabetic patients. Further, you divide them based on the BMI. So based on the BMI in each group, what is the incidence of surgical site infection in diabetics and non-diabetics? So this is by your stratification technique. Then you have the propensity scoring, wherein majorly it is by the logistic regression analysis, wherein each parameter is given a score between 0 and 1. And based on the scores, they are further classified and divided into the 2 groups. Okay. And finally, you have the regression analysis, okay, which is for more than 2 confounding factors usually. Okay, multiple confounding factors. Okay, and the instrumental variable analysis is for the unmeasured confounding factor. How do you finally interpret the data? You have association, correlation, and causation. Okay, you know the difference between the 3 terms. Association is there are 2 variables which may relate. By chance, they are related with each other, but they do not cause the other. Okay, then coming on to the correlation, there has been an increased incidence of OSA in higher BMI. So it is a quantitative measure of the strength and the direction of the relationship. Okay, there is a linear relationship between the variables first and foremost, and it can be either a negative linear relationship or a positive linear relationship. Then moving on to the causation, wherein one variable directly affects the another variable. Okay, so finally, when you report your observational studies, you should use certain guidelines, which includes your equator network and your strobe statement. Clear?
Yes, ma'am.
How much of this is probably staying in your mind and how much of this is already gone above?
No, ma'am, this will stay, I think.
Yeah, because see, to tell you the truth, I don't know how much of these will be asked in your exams. Okay, because what I know is the major topic which Dr. Amrita covered, but of course, certain other things which can be asked. That's why we thought to include in this also. And your final clinical trials, the phases of clinical trials, which is there in your IMA Plunkett, that has to be covered. I hope you all have gone through that.
Yes, ma'am.
Yeah, that is going to be covered by Danish sir. Okay, and apparently he's just stuck in something, so he told that he doesn't want to keep you all waiting, so he will record his session and he will post it in the group for all of you.
Okay.
Yeah, that's fine.
Ma'am, regarding this the journal, how do you say a journal is a good journal? So I was reading about that. So impact factor is one thing, ma'am. That is the number of citations divided by 20. Ma'am, I don't understand what they mean by index journals and what is the role of PubMed in this?
Okay, see, usually the standard indexing is your PubMed, Scopus, Embase to an extent. Majorly, it's PubMed and Scopus indexing. So these are the search engines which is available, Google Scholar Engine. These are the various search engines. So if they're going to be available in these search engines, which means, and these indexing, they give indexing for only those journals which have authenticated information, which have cross through the the ethical committee clearance. They have the, and as I told you in this, for example, in this observation study, the use of strobe and equator network, if you have used the proper guidelines, only then those journals are going to be those journals, those particular journals will accept your study, and once it is accepted, these journals will be automatically indexed in the PubMed or your Scopus. Is this what you're trying to ask, or am I not able to answer this
Yes,
question?
ma'am. Yes, ma'am. This is what I wanted.
Yeah, so usually, yeah, unless for example there are so many, also there are a lot of other journals which are just on the website but not really indexed. Okay, no, if you go through the search engine, they might even show in the search engine, in that website they will show PubMed index, they might show all that, but when you click on it, you're not able to get back to the journal. So this you need to be very careful about. So that's what they say. First and foremost, you need to follow the proper guidelines of the study, okay, experimental study. Okay, and once it is done, you have your institutional ethical committee clearance certificate, and after you upload all those things, then only the standard journals will accept your study, and once those standard journals is accepted, and hence the indexing and their impact factor increases, and those, they will be indexed in either PubMed, Scopus, or something like that.
So if I find a journal on PubMed, if I find a study, so I can be sure they followed these rules, like they have an ethical
Most likely. Most
Okay.
likely. That's why, because they are reviewed, there are a lot of reviewers of the article. Okay, like certain journals, they just publish it off. You pay the money for it, they publish it off. Just a second, I'll stop the recording.